All right, our next topic here is biomes, zonation in an ecosystem, and global weather patterns. So processes that determine weather and climate. First thing you have to understand is that weather and climate are not the same thing. Weather is what you're checking on your iPhone when you get dressed in the morning. So your weather is, oh God, it's gonna be, 100 degrees with 50% humidity. I'm gonna put on shorts and a tank top. Weather is temperature, humidity, clouds, rain, wind, speed, and atmospheric pressure. This is different than climate. Climate is the average amount of rain that an area is going to get. It's the average amount of temperature that that area gets. And it really does depend on your location in the globe, both your latitude and your closeness to a body of water. The Earth's atmosphere is divided up into 5 layers, but only 2 do we really care about. The troposphere is the layer that your head is currently in. So the troposphere is the layer closest to the Earth, and it extends up about 16 kilometers from the surface. I have seen a test question where they give you basically this graph, and you have to label the start and end of the stratosphere. So make sure that you know these numbers. In the troposphere, we have the mixing and circulation of liquids and gases, and your weather occurs within the troposphere. The stratosphere lies above the troposphere from 16 kilometers to 50 kilometers. This is where the good ozone is. And we're going to talk about that during pollution. The troposphere is bad ozone, the stratosphere is good ozone. There is unequal heating of the Earth due to the tilt of Earth on its axis. And because of that, we have the poles on either end that get very little direct sunlight. We have the temperate zones on either end that vary, they swing wildly. And so if you end up going to school in Chicago, it's gonna be 110 in the summer and maybe minus 10 in the winter. And then we have the tropical area that's the center of the globe that gets direct sunlight almost the entire time. Albedo is a term that shows up on tests. Albedo is the reflection of solar energy. So when you're out in the snow and it's like blinding because the light's reflecting up off, that's albedo. Well, if the light's reflecting off, so is the heat. And so it's not being absorbed. And so anywhere you have high albedo, you have low surface temperatures. Think about that, right? So it's bouncing off the white snow. It's bouncing off the white concrete. It is much cooler to stand on concrete than it is to stand on asphalt because the asphalt's black. The asphalt's absorbing the heat and the light. The asphalt has low albedo. We do have convection currents in the atmosphere. This is the movement of air all around the globe. This is going to move weather all around the globe. The 4 properties that determine how air circulates are density. So less dense air rises, dense air sinks. Okay, well, what's hot and what's cold? Hot air is less dense, so it's going to rise. Cold air is really dense, it's going to sink. Think about where all of your air conditioning vents are and your heating vents in California. They're all up in the ceiling, right? Because you're pumping out cold air for the majority of the year, and that's going to sink and cool the room. If you end up somewhere back in the Midwest, East Coast, all of their vents are on the floor because they're not so much concerned about cooling the house as they are warming it, and warm air rises because warm air is less dense. Water vapor capacity, warm air has a higher capacity for water vapor than cold air. So on hot days, we can have high humidity. This is the monsoonal flow that we get in August and September. Abiotic heating and cooling. So as air rises in the atmosphere, its pressure decreases and the air expands. Latent heat release. When vapor in the atmosphere condenses into a liquid, energy is released. It releases basically its heat. This forms convection currents. So atmospheric convection currents are global patterns of air movement that are initiated by this unequal heating of the Earth. And we've got 3 main convection currents. So Hadley cells are convection currents that cycle between the equator and 30 degrees north and 30 degrees south. So you have warm air rise at the equator, go up into the atmosphere, cool, and then sink at 30 degrees north or sink at 30 degrees south. Intertropical convergence is the area of the Earth that receives the most intense sunlight. It's where the ascending branches of the Hadley cells converge. And then polar cells are up above the poles, right? And they're convection currents that are formed by air that rises at 60 degrees north and south and sinks at the poles. Earth's rotation causes a Coriolis effect in our atmosphere. It also is going to cause the same Coriolis effect in our oceans when we get there. As the Earth rotates, its surface moves much faster at the equator than at the mid-latitude and polar regions. The faster rotation speeds closer to the equator cause a deflection of the objects that are moving north and south. So the Coriolis effect is this deflection of the object's path due to the Earth's rotation. Well, what is it deflecting? It's deflecting the winds. So prevailing winds are due to atmospheric convection currents and the Coriolis effect. These prevailing winds are what sailors use to get across the ocean. So these are predictable winds moving in a predictable fashion, and that's what's going to help you. Planes are going to use it as well. So if you ever pull up flight paths of planes that are going on long haul, you'll see that they don't go straight across. They're going to move with these convection currents to get that tailwind that's going to help them with fuel efficiency. Earth's axis is tilted at 23.5, which causes seasonal changes in temperature and precipitation, mostly in the temperate region. Our ocean currents are driven by a combination of temperature, gravity, prevailing winds, Coriolis effect, and kind of interrupted by the continents. And these ocean currents will affect the climate of a region. So warm water expands and rises, which rises the tropical surface about 8 centimeters higher, and then it slopes away from the equator, pushing water. If you live on the East Coast, you're going to have a more moderate winter if you're right on the coast because of the Gulf Stream. The Gulf Stream is warm water from the Caribbean that pushes north. Well, as that warm water pushes north, there's warmer air that pushes north as well. Gyres are large-scale patterns of water circulation that are going to redistribute heat and nutrients. And we have massive upwellings where water that is very nutrient-rich because no one's been feeding off of it from the bottom of the ocean come up to the surface. Our major upwelling for the West Coast is in the Bering Straits. Well, where's our most productive fishing? It's in the Bering Strait. On the East Coast, it's in the Outer Banks, up near Massachusetts, in that area. Lots of good fishing in that area as well. Thermohaline circulation, we call this the Great Ocean Conveyor Belt. So this is the movement of water between all oceans. It's a process crucial for moving heat and nutrients around the globe. It's driven by surface waters that contain unusually large amounts of salt, and the heat transports the temperature of coastal land masses. We live in an area that is greatly affected by El Nino and La Nina. Every 3 to 7 years, the interaction of the Earth's atmosphere and the ocean. So this atmospheric circulation and the ocean circulation combine to cause this El Nino or southern oscillation. The trade winds near South America will weaken. That then allows warm equatorial water to build up right there off of Chile. When that mass of water builds up, it pushes cooler water north, and it also affects all of the atmospheric conditions. It's going to affect our jet stream, and the jet stream is what brings storms across the United States. So when we have an El Nino year, the jet stream that's usually up around Oregon pushes south over Southern California, and now we've got unusually wet, rainy years. Climate change and biome shift. So as our planet warms, we are starting to see a shift in biomes. Animals and plants have ideal temperatures at which they live. And if that area warms a little bit, they're going to move to stay within their ideal temperature. It is predicted that there's an increase of 1.5 to 4.5 degrees Celsius by 2100, with greater warming occurring at higher latitudes. Not that it's going to get hotter faster at higher latitudes, but it's more evident, right? So areas that are normally frozen year-round as our mountain peaks are going to start to have periods of melt. More warming in the winter than in the summer, so it's going to be more evident in the winter. A shift in precipitation patterns. So areas that are typically dry are going to get wet, and areas that are typically wet are going to get dry. And we're going to see stronger storms in terms of cyclones and hurricanes. So we're going to see a movement of organisms in response to this shift, from the equators to the poles to escape temperature increases, and from low elevations to higher to the equator in greater moisture searches. So some biome shifts that we're already seeing happen: the Africa Sahel region, the woodlands are becoming savannas. In the Arctic, the tundra is becoming shrubland. And realize that evolution is a super slow process. And if an animal can't shift with its biome, it won't survive. And this is how we have extinction of animals due to climate change. Organisms like plants are limited in their movement due to wind and animal dispersal. They can't just get up and walk to another area. Animals can migrate further, but there's geological barriers like mountains. If you're a panda and all of your food is bamboo and the bamboo's not going to move, you're going to have issues. So what defines a biome? A biome is defined by the climate. So weather patterns, seasons, extreme weather. Temperature and precipitation are the two big ones. So we're going to define a desert by being hot with very little rain. These are what we call the defining characteristics. These are the things that when you think of a biome, what comes to mind? Latitude and altitude are huge in defining a biome. It generally gets hotter closer to the equator and lower in altitude. Ocean currents and winds will distribute heat from the equator to the poles. And productivity. We have greater productivity at low altitudes and near the equator, and you need just the right combination of temperature and precipitation to have high productivity. So here is our biomes put on a map. And so as we go from low temperature to high, we start with tundra and end at desert. As we go from low warm rainfall to high, we have desert and go to tropical rainforest. And the same map could be drawn at elevation. Zonation describes how an ecosystem is changing along an environmental gradient. So it could be from low tide to high tide. It could be from sea level to the top of a mountain. It defines the limits of an organism's niche, and human activity can alter the zonation through climate change, deforestation, and agricultural clearing. There is something called a rain shadow effect, and you guys, we see it. So if you live in Robinson or Codo or Dove, you realize that you are always under a dark cloud. That dark cloud is because of the rain shadow effect. So as air moves inland from the coast, it has a lot of moisture associated with it, right? It picks up all of this moisture in the ocean, and as it moves in, it hits the mountain, the Saddleback Mountains, right? It's then pushed up that mountain. As it goes up in the mountain, it gets cold, and now all of that moisture is going to condense into a cloud. If it gets cold enough, you'll actually get rain. When it goes over the top of the mountain, that air starts sinking. As it's sinking, its water capacity increases again. It can hold more water. And so you often have deserts on the backside of your mountains. This is true up and down California, right? So we have our coastal regions are wet. As soon as you go over the coastal mountains, you're in a desert area. All right, your biomes. I'm not going to read all of this. I'm going to ask you guys to put a chart together, but you do need to know this information. If I, on a test, give you a description of a tropical rainforest, you have to be able to come up with tropical rainforest. So all of your biomes are here, right, with where they're located and the information for that biome. Again, you need to take notes on this. So even though I'm not reading it to you, you need to know it. The last thing I want to talk to you about today is succession. Two types of succession. Primary succession occurs where there has never been life before. So think about a seamount that breaks the surface of the ocean. You now have this landmass that's never existed, and because that landmass has never existed, there's never been life on that landmass. So when we talk about primary succession, we talk about new islands, areas of volcanic, so if you think Hawaii, that's getting bigger because of volcanic eruption, that new area on Hawaii will have primary succession. And then even river deltas that dry up have primary succession. Secondary succession, you've had life before, and then a natural disaster comes through. In our area, we think that natural disaster often as a forest fire. You already have the soil, you already have the seeds, the animals already know it's a chill place to live, And so after the natural disaster leaves, we have colonization that occurs at a greater speed for secondary succession than primary. So in primary succession, we have bare rock, we have poor nutrients, not a great water supply, no soil. The first step is colonization. So our pioneer species are the first ones to be there. They're the pioneers of the area. Often this is lichen, because the lichen can break the rock down into soil. They are adapted to extreme conditions. They're often R selected, and we're going to talk about what R is in a minute. But R, you're like peppering out millions of offspring knowing that very few are going to survive, and you've got a short lifespan. Simple soil is starting to appear, some of it coming in as dust on wind. Stage 2 is establishment. So our species diversity increases, our soil is getting richer, and because of that, it can hold more water and can support bigger plants. Stage 4 is stabilization. So late coloners outcompete early species. We have complex food webs. Our K-selected species, the ones that have long lifespans, those that have very few offspring start appearing. And it ends in a complex community, which is stable and self-perpetuating. It is now at that carrying capacity for most species. And here it is in pictorial form for you. It is generally a slow process. Secondary succession, a faster process because again, we've got soil, we've got seeds, and the animals know where to be. So what occurs during succession? The size of the animals will increase, the size of the trees increase. Our food chains and food webs slowly become more complex. Our soil gets deeper and the humus gets richer. Our biodiversity increases. Our net primary productivity and gross primary productivity increase, but then they fall kind of level off. So you're gonna have a spike in it and then it's gonna level. And our respiration ratio falls. We can arrest succession at any point. We often do this for farming reasons. We can do it because we like a prairie full of flowers instead of a mature forest. It's usually human activity that is doing this. There are disturbances within our ecosystems. Think about a tree falling in a forest that now creates this open space of light, and our pioneer species come back and it's a little meadow, and then it slowly matures back into a forest. All of that disturbance adds productivity and diversity to our ecosystem. Last but not least, R versus K species. It's a term you're going to hear throughout this course. K species are big animals that have a long lifespan and produce very few offspring within that lifespan because they mature to sexual maturity very late. They have a lot of maternal care, so their offspring tend to survive. This is different than our species. It's a smaller organism, short lifespan, millions of offspring. Very few of their offspring survive because they have no parental care. Think about spiders versus elephants. Spiders are R species, elephants are K species. We have our survivorship curves. So our type 3 survivorship curve is an R strategist, right? Millions of offspring, very few survive to reproductive age, very short lifespan. Type 1 are K, very little offspring, but most survive. And then this type 2 is very rare in nature, moderate death rate, and individuals are dying at every age. So let's look at the picture. Which one of these are R species? In this picture, the cockroach, the ant, and actually the mouse is an R species. Lots of offspring, very little parental care, can handle changing environments very well. If we have nuclear winter, the cockroaches are still going to be here. K species are our mountain lion, elephant, and human. All right, guys, that's it for today. Make sure that you fill out your study guide, and I will talk to you guys next time.